Hi everyone, it's time for some more organic chemistry. We are working in Key Concepts, Part 2, Unit 3, Part 2. And try to set up the screen here. Lots of stuff all over the place. Okay, so we're in the middle of alkynes, the triple bonds. And there was a previous video about multi-step synthesis. So take a look at that. It's a nice strategy for how to design the creation or synthesis of large molecules. And we're not going to do that large of molecules, but if you wanted to make like the new anti-cancer drug, it's a good way to kind of plan it out. So take a look at that video. Today, however, we're going to move forward and just wrap up the triple bond reactions, and there's only 2 left. And it's kind of the same thing. So the last 2 reactions of the triple bond are oxidative cleaving reactions or oxidative cutting reactions. You saw these already. I scroll the screen over a little bit. We'll review these same reactions with alkenes, carbon-carbon double bonds. So I think we took propene before. And then if you treat it with ozone, follow up with zinc in dilute acid, H3O plus, just notation for acid. It could be HCl, it could be sulfuric acid and water, whatever. And what happens is you just cut that double bond into 2 pieces. I'm going to talk about doing a karate chop, or use your butcher's cleaving knife and chop a piece of meat in half. It kind of bleeds. So put the cotton balls at the ends. Yeah, there's one cotton ball, and there's another cotton ball. And those are oxygen atoms in the molecules. And what you see then is that what used to be an alkene turns into an aldehyde here. And this is also an aldehyde, but a special one, formaldehyde. And you put a little plus sign if you like, say, hey, you make 2 products from 1. I call that mild oxidation. A lot of authors of organic textbooks call it mild because it just stops there. Nice, to the point. Chop the double bond in half, cap with those, you're done. There's something else called strong oxidation, and typically that's done with potassium permanganate. And it's called strong because it doesn't stop at this stage. The oxidizing agent, potassium permanganate, attacks the products and turns them into carboxylic acids. So again, this is review with alkenes, carbon-carbon double bonds. Use a little permanganate under acidic conditions. You chop it in half. You do get the same intermediates. So, sorry, same products, but they are intermediates now. You get an aldehyde. You get formaldehyde if you cut propene in half. But the problem then is that permanganate attacks these molecules again, oxidizes yet again, and inserts an O where the aldehyde hydrogen was, and now it's a carboxylic acid. Carboxylic acid. And if you want to be technical, you get O's inserted into these carbon-hydrogen bonds also. But then this molecule is actually, well, 2 H's, 1 C, and 3 O's. That's carbonic acid. And that is unstable and falls apart to produce water and carbon dioxide. And the organic chemist only cares about the molecules containing carbon. So we would say that 1 propene reacts with permanganate to form acetic acid, this molecule, plus carbon dioxide. Okay, so that was review. Turns out you can do the same reaction with the triple bond, but you go straight to the carboxylic acids, even with ozone. So that's the pattern we'll have to remember. Before I move off of this page, I want to just make a quick note. I will not ask for the mechanism of these reactions, and I'm not going to go over it here. They're oxidation reduction type reactions. They're not helpful for predicting the products. So we're going to skip them. So compare and contrast. We just reacted alkenes with ozone and permanganate. Now let's take the alkyne functional group. And I like zigzagging my triple bond. I should not do that, right? A carbon-carbon triple bond is sp hybridized. The bond angle is 180. It's a linear shape. It has a linear shape here. I'm supposed to do this. The problem is, especially when I'm grading and I look at other students who have handwriting just as bad as mine, and I see something like this, it's kind of like, do you mean this? Or do you mean this? When they draw that. Okay, so then I tell my students, please zigzag your structure. So then it's clear. This molecule has 3 carbons. This one, it's hard to tell because the handwriting is bad. Okay, so forgive me for drawing the wrong shape of my triple bonds, but I do it just to clarify how many carbons are in my skeletal drawings. All right, compare and contrast. We got our double bond over here with ozone. Switch by adding another pi bond to make it an alkyne triple bond, but use the same reagents. Ozone followed by zinc and acid, and you still get the same pattern. I had a student point this out to me, and I like it, so I'll show it to you. If you get the 2 pieces again, 2 triple bond, no, I'm sorry, this is half of the triple bond here, and the other half is just a little fragment of a triple bond. And then you say, hey, I'm going to just cap it with cotton balls. Well, remember oxygen, HONC, 1, 2, 3, 4. Oxygen prefers 2 bonds. So you're really not going to cap the triple bond with an oxygen. You can only really cap 2 of the bonds. So you need another O for the 3rd bond. Oxygen wants 2 bonds, so make it an OH group. And then this funny drawing is supposed to be the carboxylic acid, which is what we got with permanganate. How about that? And this one turns into carbon dioxide. I don't know what you want to do with capping the O's, but you get the same product you did with permanganate and alkenes if you start with a triple bond, whether or not you use ozone or permanganate. So same pattern. If you use permanganate on an alkyne, we're doing triple bonds. So if you use permanganate on the triple bond, you also break it up into the carboxylic acid and carbon dioxide. So it's pretty straightforward. The trickier ones are the alkenes, right? So if you start with a double bond, you get different products. Ozone makes aldehydes and ketones. Permanganate can make ketones too, but it makes carboxylic acids and carbon dioxide, depending on the structure. Switching to the triple bond, doesn't matter which reagent, you just get carboxylic acids and carbon dioxide. So it's a little more straightforward with triple bonds. Nice. And that ends the reactions of triple bonds. So yay, are we done with unit 3? No. There's more functional groups. So go back to previous videos, kind of review the triple bond reactions, the alkynes, and then get comfortable with those. Add these 2 in place, and then you're ready to move on to a new functional group. I think it's alkyl halides. But one more detail. Let's first talk about how to name molecules containing triple bond. Okay, so switch over to naming. And we got common names still. We got Iupac names. Thankfully, there's only one common name that I need you to know regarding a triple bond. And that's the smallest molecule containing the triple bond. 2 carbons, triple bond together, has a common name, acetylene. You may have heard of welders using acetylene in their blowtorches. Yeah, same stuff. The Iupac name is ethyne, right? Methane, ethane, propane, butane. Molly eats peanut butter. 2 carbons is the ethyl, ethane. Okay, but change the ane ending to a Y-N-E and you get ethyne. That's the Iupac name. Yeah, but before Iupac convened and the convention was held to make up these naming rules, people already knew about this molecule and they called it acetylene. And the name really sticks. I rarely hear scientists, chemists using ethyne. So know what acetylene is. It's the smallest triple bond, carbon-carbon triple bond. Okay, that's the only common name. What about Iupac Names? Well, hopefully you've gotten comfortable with the naming rules. I just kind of cut and pasted over here real quick. Just follow these naming rules with one little change, two little changes. So the naming rules for Iupac, the standardized names, International Union, the pure and applied chemist, that procedure. First, find the longest chain of ring with the highest priority group. And I don't expect you to memorize the functional groups. Just know that the more pi bonds, the more important it is. The more oxygen, the more important it is. That's the trend. And then after you find the parent chain with the most important functional group, count up the carbons of that longest chain of ring. That's the parent. Change the ane ending to the suffix that tells the reader which functional group is most important. So the functional groups we've seen so far are alkanes, ane ending. We've seen, and that's a carbon-carbon single bond. We've seen alkenes, that's a carbon-carbon triple. And now we're getting alkynes. There's a pun in there. We're seeing all kinds of carbon. That was bad. We've also seen the halides, but those are prefixes. Alkyl halides, really. That's a functional group. So we've seen these four functional groups. These don't have a suffix name. It's always, the fluoro, chloro, bromo. It's a prefix. Anyways, know your suffixes, alkenes, alkynes. And we got the parent name. Step 3, you want to number that chain of ring so you can get to that most important functional group as fast as you can. And after you do that, if you have a tie, go after the first branch or first extra group, maybe a halide, whatever. And if that's tied, go to the second chain, check second branch, whatever. You know the drill. All we're doing now is just adding the triple bond to potential, it's another suffix to remember. And the naming rules are the same. And then after you've numbered the chain, go down the chain, name every extra group, use a prefix. Step 5 is add a number so you identify where it is. Yeah, assign every functional group, alkyl branch, whatever, a number. Oh yeah, and the little thing, but when you have a double bond or a ring, you might have to use cis or trans. And if they don't work, you might have to use E and Z. You might have to use R and S for a chirality center. Okay, and I think that's everything. The last thing though is put your prefixes in alphabetical order. Okay, so I know that's a lot, but you've also had a lot of practice with alkanes, single bonded carbon, and alkenes, double bonded carbon. So just don't hit delete in your head. Keep your knowledge of naming from before and just carry it forward. And just add triple bonds. That's all you have to do. So let's try it out. So here's a molecule. Hey, there's a triple bond in it. Surprise. Step 1, find the longest chain. Okay, so I got 1 carbon here, then 2, 3, 4, 5. That's a possible chain. We can start here again. 1, 2, 3, 4, 5. Go down there. It turns out we got 4 carbons here. And then whether we go to this methyl for 5 or down the methyl for 5, it's a tie. So I'm just going to keep going straight across. There's my parent chain. It's a chain of 5. And Molly eats peanut butter. And then the pentane, hexane, heptane, all the good stuff. 5 carbons means pentane. But the most important functional group is the triple bond. So drop the ane ending and add the YNE, the pentyne group. There we go, and that's the parent name. That was step 2. Okay, step 3, number the chain. Well, here's a chain of 5. So our choices are, is this carbon 1 or is this carbon 1? And the answer is, which one gets us to the functional group that's most important as fast as we can? It's this one. So you don't number from the right side. Over here, if you start numbering, you can get to the triple bond by number 2. Then numbering, let's see. You walk down the chain, add up, list all the extra groups with a number. So carbon 1, 2. On carbon 2 begins the double bond. sorry, that's a triple bond. On carbon 2 begins the triple bond. And like, and like the double bond, you have a choice. Do you want to put the 2 in front of the parent to say where the triple bond begins? We did that for the double bonds, remember? Or you can keep the number right next to the suffix so it's clear where the triple bond begins. It begins on carbon 2. And then it must go to 3. That's the assumption. All right, but on 4, there's also a branching methyl group. Okay, squeeze it in here. I'm going to. And there's the full name. Methyl. 4-methyl pent 2-ine or 4-methyl 2-pentyne. There you go. So it's kind of nice. As long as you know how to name the double bond, just you got the triple bonds. Unless there's both a double and a triple bond in a molecule. Okay, so that's new. Just to make sure we're all on the same page. Here's a molecule with 2 triple bonds. So let's name this. Step 1, find the longest chain. Well, there's no branches. And this one, hopefully it's pretty clear. You know, it's not hand drawn, so yes, it's pretty clear. There's 1, 2, 3, 4, 5, 6, 7, 8 carbons. 8 carbons is octane. We're going to drop that and add the Y end in. Y and E ending. And then, so that's a parent name, octine. I know some of you are saying, wait, that's not quite right. You're right. We'll get to that in a minute. We'll fix this parent name. Step 3 is number the chain. And you want to do so to get to the most important group as fast as you can. So do we start on this end? If we did, it'd be 1, 2, 3, and we hit the triple bond on by carbon 3. And you're always saying no. Start at this end because immediately you find a triple bond on carbon 1. So this is the correct way to number the molecule. Cool. And then just walk down the chain, list where all the functional groups are, all the branches. Well, there's only the triple bonds. The triple bond begins on carbon 1 and on carbon 5. So your choices are 1, 5, oct. Well, there's 2 triple bonds. Like if there was 2 methyls, you'd say dimethyl. So you say diine. And then Iupac wants you to slip a little A in here so it rolls off the tongue a little more easily. Instead of saying 1, 5, octdiene. Octdiene sounds like I'm hesitating. Octadiene is a little better. If you forget the A, no points lost. But if you look it up, that's what you'll see. And the alternative is actually, the alternative is to keep the numbers right next to the suffix. So you'll see octa 1, 5, let's make sure it's clear. Diine, there we go. And again, if someone said oct 1, 5, diine, I will give them full credit. I know what they're saying. I know what they're naming. Cool. Okay, we're good on that, I hope. Let's deal with the case where there's both a double and a triple. So do we get any help with that? Yeah. Let's go back up to our key concept. Here's what you need to know. What Iupac decided in a committee by vote, they said, you know what? When you're numbering those carbons, we're going to let the alkene and alkyne have nearly equal priority. And it just violates what I said it before. I said, wait a minute. I thought we said the functional groups are ranked based on more pi bonds, more important. And Iupac said, yeah, except for the carbon-carbon double and the carbon-carbon triple. They're going to be the same. Whatever. Okay, then what? Well, if they're equal, nearly equal, then all you have to do is number the chains so you can get to any pi bond, whether it's a double bond or a triple bond as fast as you can. So just get to one of them. And that's the correct numbering scheme. And then if it so happens that if you come in from one side, you come in from the other, and you hit a double and a triple at the same number of carbons coming in, you have to decide which way do we do it? The tiebreaker goes to the double bond. All right, so that's how the game is played. Those are the rules. Let's give it a go. So I got 3 examples here. Let's name these. Step 1, find the longest chain. Okay, well, it's a straight chain with 2, 3, 4, 5, 6, 7, 8. These are all octane. But then we drop that. And then wait, there's a double bond in here, so that's an ene. And there's a triple bond, so that's an ine. So which suffix do we use? Well, Iupac just said they're nearly equal. They don't outrank each other, they're tied. We have to use both. Or use them both. And actually, you have to say in your name that there's a double bond and a triple bond present, and there's no prefix for these 2 functional groups. You have to use 2 suffixes. It's not going to be the first time. We're going to have lots of, as we see more functional groups, we'll start throwing in double suffixes. So we'll get used to it. Trust me. Just through repetition. All right, we're at step 2. We got the parent. It used to be octane, and we're adding the ene, the ine. And in case you're wondering, yeah, alphabetical order, when we put this whole thing together, it'll be ene before the ine. Okay, step 3 is the number of the chain. So what do? We get to any pi bond as fast as you can. So is it 1, 2, or is it 1, 2, 3? Yeah, not this way. We get to the double bond by carbon 3, but so we're going to come in from the other side. Get to a pi bond faster by numbering on the left side. Why I got 2 6s? Because I'm not thinking. There we go. All right, so then let's construct the name. Walking down the chain, 1, 2, oh, the triple bond begins on carbon 2. 3, 4, 5, the double bond begins on 5. Uh-oh, if you have a double bond, what do we have to worry about? Cis and trans. So is this double bond cis or is it trans? What are the 2 identical groups and how are they oriented about the double bond? Well, we got an ethyl group here and a crazy 4-carbon group with a triple bond on it. They're not identical. Instead, look at the hydrogens. One hydrogen's here, the other one is there, and it's on opposite sides. They're across from each other. That's trans. So the double bond's actually in the trans. If you want to use E or Z, this one's E. You get to use either one. But those are all the groups. We stick the trans out in front. That's where cis and trans goes. You start it off with cis and trans. And then any prefixes? Nope, there's no ethyls or chloros or anything like that. So then it's the parent. And then alphabetical order. It's going to be 5-ene and no letter A. Don't worry about it. If we jam this ene next to the oct, that would be fine. But if you jam the I next to here, you have an E and a Y, 2 vowels together. We're supposed to drop the E. Don't panic. If you leave the E in there, full credit. But there's the name. This is transoct 5-ene 2-ine. And it's a really good idea to keep the number with the suffixes, because if you pull the numbers out in front, how do you know which number goes to which? Or you'd have some doubt. So you have to keep the numbers with their suffixes. There's the first one. We're done. Let's try the next one. Okay, well, 1, 2, 3, 4, 5, 6, 7, 8 carbons is octane again. In the molecules, both an ene and an ine, a double and a triple bond. Let's number it. Well, try to get to a pi bond as fast as you can. So from this end, on carbon 2, I'll hit a pi bond. If I come in from the other side, 1, 2, 3, pi bond on 3, nope, that loses. So we're again numbering from the left side. And if you drew the molecule the other way, doesn't matter, you come in from the side that gets you to any pi bond as fast as you can. You know what? I got a little red flag going off in my head. When I said any pi bond, I mean today, the only pi bonds we know about are alkenes and alkynes. Carbon-carbon double bonds, carbon-carbon triple bonds. But you know there's other functional groups with pi bonds. They actually outrank the alkenes and alkynes. So it won't, when we look at other functional groups of pi bonds, we'll actually try and number to them first and ignore the double and the triple bond, because the other pi bonds will outrank these. Okay. But right now, between a double and a triple bonded carbon, find either one of those pi bonds fast you can. And if you're coming from the left side, we get to one fast here. That's the right way to number it. So in this case, the double bond started on 2, the triple bond starts on 5. What about that double bond? It's still trans. Hydrogen's opposite side of the double bond. So the name still has trans. Still 8 carbons, still oct. Alphabetic order, so put the E to ene. If you put the E here, I will just ignore it as I grade and you'll get full credit. And then the triple bond, the ion group starts on carbon 5. That's the name. Last one here. Okay, there's still 8 carbons. It's octane. The functional groups are tied. The most important functional groups are tied between the ene and the ine, double and triple bonded carbon. Which way do we number though? So if you come in from this side, 1, 2, ooh, we get a pi bond on 2. If you number from this side, ooh, we get another pi bond on 2. It's a tie. Which one do we go to? Iupac says the tiebreaker goes to the double bond. So we come in from the right side this time because the double bond just slightly outranks the triple as a tiebreaker. Cool. And let's see, this double bond that starts on carbon 2 is still trans. There's still 8 carbons. Double bond starts on 2 here. And the triple bond began on 6. So I moved the triple bond, so, right. But there you go, that's the chemical name. Nice. What else do we have here? Okay, so we dealt with the triple bonds, how to name them. The last molecule, the last reactions were the chopping reactions, ozone and permanganate on a triple bond. So in Unit 3, we're also going to discuss alkyl halides. And we actually already have a head start. So we have 2 reactions here that are review from Unit 2, where we made where we made alkyl halides, molecules containing halides already. So the first one we saw was electrophilic addition of an alkene with HCl or HBr or HI, or you could use phosphoric acid and potassium iodide. We also said you could use acid and water as a reagent, but remember that makes an alcohol. And right now we're focusing on methods to make alkyl halides. So that's why I didn't list this water and acid here. It doesn't make an alkyl halide. So the focus is what reactions make alkyl halides? Carbon containing a halide, and this works, right? And it goes by Markovnikov addition. I'll just say Mark. It has carbocations. Ooh, that's not fun, because that usually makes more than, not usually, it sometimes makes more than one product. That lowers our yield. We have more things to remember. It's not pleasant in the lab, so we try to avoid that. But here, let's see, Markovnikov's rule says the carbon, the alkene carbon with more hydrogens gets the hydrogen. So the pi bond will grab this hydrogen, put it at the end of the chain to create the carbocation, and then the chlorine will attack that carbocation and go to the secondary carbon, and that's the product. Cool. You saw that. You probably saw it on the exam too, for Unit 2. And then we also saw this reaction, free radical halogenation. The mechanism was initiation, propagation, termination. Yep. When we did our video, we actually talked about this specific reaction with methane, reacted with chlorine. And I don't remember if we used light or if we used the Greek letter delta, which means you heat it up to make the reaction go. The initiation step, he uses heat or light. And then what you do is it's substitution. Take away one of the 4 hydrogens, put on a chlorine. The missing atoms form a byproduct, but hey, there's no carbon there, so the organic chemist really doesn't care about that. And then we said, you don't have to just do this methane, you can use any alkane. And turns out if you get a mixture of products, it's not very good. So if you decide to use butane, that's not a really good way of making 1 chlorobutane, because this reaction will also make 2 chlorobutane, right? And whether you get the chlorine at the end depends on whether you pull off these hydrogens, the primary hydrogens, right? So these, so if you ask the carbon, hey, how many carbons are you attached to? This carbon says, I'm attached to 1, I am primary. This carbon, same response. So if you pull off one of those 6 hydrogens in this mechanism and substitute with the chlorine, you get this molecule. But if you go after the secondary hydrogens, there's 4 of them there, then you get the 2-chlorobutane. And at first glance, hey, there's 6 of these, 6 primary hydrogens, and there's 4 of the secondary ones. You know, just statistically, shouldn't we have chlorine showing up at the end of the change more frequently? There's more opportunities there to do a substitution reaction. Well, that's people talking, and nature, she makes the rules, and she says, nope, I'm going to have 70% of this molecule, only 30% of that. That's a typical ratio we see in the lab. It's like, well, what's going on? Why are you saying most of the time, 70% of the time, you want to pull off one of these secondary hydrogens and not go after the more, you know, the more plentiful primary ones? It's because nature's kind of lazy. She's taking the path of least resistance. She's going the route that leads to the most stable products or the most stable intermediates. So in the mechanism, the intermediates are radicals. And when we went over the mechanism, I guess I should just put it here really quickly. For this reaction, we said heat or light splits the chlorine radical, splits the chlorine molecule into 2 radicals. That's initiation. Then we said the chlorine radical will react with the CH bond of methane. So this is CH4, but I'm highlighting one of the carbon-hydrogen bonds. And we said that this bond gets broken homolytically, fancy word of saying equally. 1 electron goes to hydrogen, 1 electron in that bond goes to carbon, and then these 2 groups, the hydrogen and the chlorine, form hydrochloric acid. That's 1 product. And then you make a carbon-centered radical. You make a free radical. Okay, and then there's more parts to the mechanism, right? But this is all I need to explain the 70-30 ratio, because the mechanism's the same in this reaction. Heat this up. Well, it looks like they use light. Heating, you know, shining light on chlorine will split into 2 radicals like we did up here. The radicals will then attack butane. And there's a choice, right? So if the radical, chlorine radical, grabs a hydrogen that's primary, then you get a radical that's also primary. Yeah, so that's what happens. Pull off this hydrogen, and what's left behind is a carbon with the dot, with the radical. But if you pull off one of these secondary hydrogens, then you get a radical that's secondary. The dot's on the carbon that lost a hydrogen. And now let me ask you, if these were positive charges, they're not, but if they were, is there a difference in stability here? Yeah, right? You remember that tertiary carbocations are most stable, secondary then falls behind, and primary is even more unstable. Primary carbocations are more unstable than secondary. So nature prefers secondary. And it turns out the radicals follow the same pattern. Yes. Okay, so what we knew about carbocations, we can apply somewhat to the radicals. The difference, though, is the radicals do not they're less likely to rearrange. We're not going to worry about radicals rearranging. So yeah, that was my first worry when I heard about this, but don't worry about that. Here's the bottom line. The radicals follow the same order of stability as the carbocations, which means that if you have a tertiary carbocation, so the R just means the rest of the molecule. If I make that a carbocation, so down here in the bottom, we'll draw some carbocations. This one's tertiary. That's more stable than secondary. So the R are just groups with carbon. They could be methyl. They could be butyl groups. They could be iso, propyl groups, whatever. But this carbon with the dot is immediately attached to a total of 2 carbons. It's secondary. So this will be a hydrogen. And that should be a plus. We're talking carbocations here. And then up here, if there's only 1 carbon attached to the carbocation carbon, that's primary. Secondary, primary, tertiary. And that's what we studied before in Unit 2. Oh, and I think we also said methyl is even more unstable. There's no carbons attached to help stabilize that carbocation. And then what we need to know now is that radicals follow the exact same pattern. Tertiary is more stable than a secondary radical. Secondary is more stable than primary, more stable than methyl. But you know what? We just finished a chapter on double bonds, so now we're going to include a couple more. If you put the radical or the carbocation on a carbon involved in a double bond, oh my gosh, nature hates it. There's something about sp2 hybridized carbon that just cannot deal with a radical or a carbocation. They are very unstable. Nature will avoid them. So usually we just don't see these. Nature just says, nope, that's too unstable. It takes too much work to make them. The carbon is just too unhappy. We ain't going to do it. On the other hand, if you put that radical or the carbocation 1 carbon away from a double bond, nature says, yeah, let's do that every day. Let's do it more often than when we put it on a tertiary carbon. Why? Because there's resonance stabilization. So the double bond can swing over. So right now this carbon only makes 3 bonds. So the pi bond can actually move. If you want to draw a curved arrow to show the motion, you can. You don't have to. So the double bond could swing over. And now if the double bond's on the right side, this carbon at the end has 4 bonds, no positive charge. It's nice and happy. It's nice and stable. The other carbon, though, is like, whoa, what happened? I have 4 bonds. The pi bond left. Now this carbon is positive because it's the only one, because it's the carbon that doesn't have 4 bonds. It only has 3. And then it just bounces back and forth. The pi bond just bounces back and forth. And if you watch this carbon at the left end, half the time on average, it's nice and happy with 4 bonds. Half the time it's kind of cranky with 3. The other carbon, like half the time it's positive, yikes, and half the time it's fine. This tertiary carbon is positive all the time. So to share it this way is more stabilizing. Resonance stabilizes intermediates. And nature says, okay, the carbon next door to a double bond is a great place to make a carbocation or a radical if you have the choice. Just don't do it on the carbon double bonded. Yeah? Cool. Okay, so we're going to use this trend in our next video and a few more times throughout the semester. But you know what? That's enough for now. I'll see you in the next video.